Hello, welcome to this video on geospatial imagery, and we'll be talking about the origins of imagery and GIS and remote sensing and what it's all about. This coincides with Chapter 9 in the text, Chapter 9. And so it would be good for you to read Chapter 9. Now, up until you get to page 316, and 316 starts with how can you make measurements from an aerial photo. That's optional. You won't be tested over that. You won't be expected to make measurements from an aerial photo, but it's actually kind of interesting. So if you're interested in it, I recommend that you read through that and maybe give it a try. Practice with some aerial imagery if you happen to have some. But this is not a required part of the book. That's actually called photogrammetry, which is not a part of this course. So let's get into imagery. It's one of my favorite things in GIS is looking at satellite imagery, aerial imagery flown by in an airplane or helicopter. It's just really interesting to me. It always has been. I was always that person that when it came time to get a seat on an airplane, I was the one that wanted to be right there with my head, pressed up against the window looking down. So let's get into this. What we're looking at in this bit of imagery is Concordia University out west of Austin, near Lake Travis. And what you're seeing here, these are trees, these darker areas here, those are oak trees and deciduous trees, the kinds that lose their leaves. And these green ones, those are green puffy looking things, those are evergreen trees. We've got a parking lot here. These are buildings. You see me looking over this way because my camera's right here and my actual screen is right there. We have a pond here. This is where they're building the baseball field at the time. So let's get into what it's all about and how this whole imagery thing got started. So when we are looking at aerial imagery, we're doing something, we're participating in a field called remote sensing. And the name came from this Evelyn Pruitt. She worked at the Office of Naval Research in the 1950s. And what it is that we call it the science and art because it's not a pure science. There's a level of interpretation there. It's the science and art of acquiring information, spectral, spatial, and temporal, about material objects, area, or phenomena without actually coming into contact with it. So if I am researching this little rubber ball, I take it, I'm feeling it, I want to know if it's smooth or rough or what's going on. I'm touching it, I'm coming into contact with it. That's not remote sensing. If I am getting information about it remotely using a camera, using some other tool that gives me information about it, then that is remote sensing. So remote sensing is not just referred to the use of video or camera or film or digital imagery. There are a number of ways that you can remotely sense something with your ears, with a microphone and speaker. You are recording sound. That's another way to investigate things remotely. All right, so which of the following of these are remote sensors? We've got a pH meter. The pH meter must come into contact with whatever you're measuring the pH of, so that could not be a remote sensor. That's a satellite dish. It is picking up data from the sky. That's a remote sensor. Camera. What do you think? You're coming in direct contact with the camera perhaps by holding it, but the camera is sensing an object in the distance, so that's a remote sensor. Thermometer here, fever thermometer. You've got to place that under your tongue or in other unfortunate places, and it must come into direct contact with whatever it is you're trying to measure. And your ear. Your eye, for that matter. These are remote sensors. Your ears and your eyes are both considered remote sensing tools. So a little bit of history. This, you are looking at this right here. This is the first photograph that remained. There may have been some before this, but this is the only photograph that actually remains from early days of photography. This was taken by a Frenchman named Joseph Niepce. I'm not sure if that's how you pronounce it, but that's the man who took the picture. This was left. It was a camera he had built. I think they called it a camera obscura back then, and he left it open, left the shutter open for a long period of time. And I think this is a roof from his window. He's looking down at another roof. I'm not really sure what we're looking at there, but that's the first picture. So a little bit of history about behind remote sensing and aerial photography. There's the first black and white photography was in 1827. 1858, first aerial photo. This is not actually it, but this is in Paris, and it is an aerial photo. But the first aerial photo was taken from a balloon over Paris. I don't know if that still exists, but that's the date of that. The 1860s to the 1900s, aerial photography was taken from balloons and kites. They'd send a kite up there and with a camera on it and take pictures. In the Civil War days, there would be a balloon or a kite hovering over the battleground or hovering way up high and trying to take pictures of the enemy on the other side of a hill. So it's been used for military aspects and civilian aspects for quite some time. So this is from World War I. Excuse me, I still have a little bit of hoarseness left from last week. And what you see here, pardon me, I keep looking over this way, but what you see here, these are trenches. And this is what you would call no man's land. You've got, I believe this is the German trenches over here. These are the Allies, our Allies trenches here. And you can see how they dug these. In and back and forth and back and forth. And the way that they advanced was to build another trench and poke up your head like a little prairie dog and shoot at the other people on the other side and poke your head back down. This is the war that seemingly would never end. And part of it was because of this trench warfare. I'm not going to get into the history of the war, but this is some aerial photos from that war. Okay, between the wars, Germany was actually experimenting with using pigeons. They built this little vest and put a little camera on the pigeon. And you can see the picture taken above this castle with the pigeon wings. Actually, the pigeon was flapping, and the camera was being worked remotely or on a timer. I can't remember, but this is from a magazine in 1932, describing how the Germans were using aerial photography with pigeons. This is looking straight down at an intersection. By the way, that is 1 year before Hitler came to power. Just a little bit more of a context of what's going on historically. And then here's a very large camera from an airplane. While this guy's flying the airplane, and this one back here is pointing the camera down to get more of the scenery down below. Okay, so what you're looking at here is the first actual image from space. This was taken from the Corona 1. The Corona 1 was the first U.S. spy satellite. Now, Sputnik had done this thing in 1957. It came from Russia. It freaked out the Americans because, oh my gosh, the Russians are in space. In space. We're not there. The Russians are there. So America freaked out. So thus began the space race. And America wanted to not only get into space, but send up some cameras. And so they had this thing called the Corona 1 program, the first spy satellite. And this is I think this is Cape Canaveral. And this is a runway. There's a parking apron, a parking lot. This is the first picture coming from Corona. Now, this is not Corona. This is an airplane. What this airplane is doing is It's got this netting behind it, and whenever Corona would, if everything was analog and film back then, so whenever Corona would use up a canister of film, it would eject it, and it would come, gravity starts bringing it back down to Earth, and so you had to have a really good pilot here to fly this airplane along with this net behind it, woo, back behind it, and hopefully fly in just the right place and the right time to catch that film canister. I'm not sure what happened if it dropped it, but anyway, there you go, right there. The plane catching that canister. All right, so, and that was the first image from space. Being back, well, it wasn't being back to us, it was dumped off in the camera. This is actually the first official image from space. That Corona picture was classified up until the 1990s. It didn't exist as far as you and I were concerned. It was a government thing. They kept it a secret until the 1990s. As if we did not know that there were spy satellites flying around in the 60s and 50s, but anyway, they kept it a big secret. So the first official, the first recognized image from space as far as civilians were concerned was from Tyros, 54 years ago. And this is looking back. It was a weather satellite, and so its purpose was to look at the clouds. And so these are the first times we're getting images of the clouds and hurricanes and what's going on a big global basis from a satellite. So pretty cool. Now, during the 1960s, we had this thing called the Apollo program, and some of you may remember it, some of you may not. But the Apollo program was this goal, that what we had to get us to the moon. Big time goal. President Kennedy says we're going to get to the moon and back safely before the end of this decade. So that was the Apollo program. So as we kept sending the astronauts up into space to practice this whole getting to the moon thing, we were getting images of the Earth being back to us back here on the planet. And some of the government officials, actually the director of the Secretary of the Interior, his name was Secretary Udall, he thought this would be great, that if we could get pictures of the Earth from space, it would be a great way to help us manage natural resources. And so he promoted this Landsat program, which we still have going on right now. So it started in 1972. Its purpose was to take images of the Earth, specifically not for any kind of war mission, not for any kind of we're going to go to Mars mission or the moon, but to figure out what's going on this planet. It was an environmental research program. Really cool. Anyway, so a little bit of history of the Landsat. We had Landsat once was launched in 1972. First system to provide any kind of views of the Earth for the purpose of viewing the Earth, and specifically land, in our country's history. We had Landsat 1 through 5, and then in 1993 we had Landsat 6, and it failed to reach orbit. It got to a certain height, and then it blew up and fell back to Earth. Then in 1999, this was when I was actually getting into this whole remote sensing thing, was in 1999. So I was into it, and we were excited about the launch, and it was a great mission until about 2003, and it began to fail. So it still works, but we get the images that come back are not the best. There's like strips in it where you can't see anything. Okay, so here's what we've got. Oh, I've got coming soon up there. I should not say coming soon. I should say it's there. Landsat 8. Before it was launched, it was called Landsat Data Continuity Mission. It's hard to say. And once it reached orbit, it was called Landsat 8. So we're going to call it Landsat 8 until it made its orbit. I guess it was sort of we don't want to jinx it thing. And it's a really neat satellite. When it was launched actually during one of my GIS classes. And so we took the time out in my GIS class to, we could watch it online. It was so cool. I'm such a nerd. Anyway, so Landsat 8 is up there, grabbing images of the Earth right now, even as we speak. In fact, it probably flew over here somewhere near here. It's 11:30 when I'm speaking, and it comes over somewhere in the United States, in the North American continent. It will fly over some part of the U.S. Around 10 o'clock every day. Just a little bit of trivia there. All right, so just a little bit to show you the difference in quality going from 1973 to 1988, and you can also see the difference in the land there. This is Mount St. Helens in 1973. This is Mount St. Helens after it had blown its top in 1988, and you can see the difference in clarity. And today's satellite, Landsat 8, does not necessarily have that much more. It's not that higher in spatial resolution than this one here, but it's got a lot of other really great things about it. It has better what we call spectral and radiometric resolution, which means that you can get more data from it, even if you don't necessarily see visually what's coming back from it. Here's some more satellite imagery. This is using radar. It's picking up on the reflective radar waves. You get sunlight coming in from the sun, and that brings, and you're actually getting radio waves coming in from the sun, and this is reading the reflected radio waves. Once those radio waves from the sun hit the earth and reflect back, this is what this is picking up on. This is the Mekong Delta in Vietnam. This is Canada's satellite, RadarSat, and this is a Russian satellite from 1998. It's Area 51. The Russians were checking us out there. This is Nevada. And here is, this is the GOI-1 satellite launched in 2008. And this is off the coast of Dubai, I believe. And you can see this is where they're building up. They're taking sand and building this crazy-looking island. I think they call it the Palm Islands. Very rich people buy property on this man-made island and live there. So, and then in 1999, that was a big year, and in 2001, those were two big years because for the first time, private industry were sending up their own land imaging satellites, and private industry had been sending up satellites for communications, radio, TV, all of those things. But for the first time, we had private industry sending up land observation satellites. So how it works, it starts with the sun, and the sun emits every part of the electromagnetic spectrum from cosmic and gamma rays all the way to radio waves, as well as visible. This is why you and I can see. Now, you and I can see the wavelength from purple/violet to red, which is 400 nanometers to 700 nanometers. Now, if you were taking the raster course, you would have to know the nanometers and all of this, and you'd have to memorize the electromagnetic spectrum. I'm not going to ask you to do that because that's not really within the scope of the course. But what you should know is that all of this does come from the sun. Most of this, the ultraviolet to cosmic and gamma rays, that gets blocked out from the Earth by the atmosphere. So what makes it through is everything from blue, violet, blue, green, orange, yellow, and red, infrared, and microwaves and radio waves. Those all make it through. And 5 things happen to those kind of waves on their way to the Earth. Those short wavelengths, gamma, X-ray, UV, they get blocked out. Some of the UV does. Some of the UV makes it through. That's why you get a sunburn. That's what's getting you. Some of it's scattered. This is why the sky is blue. What I mean by scattering is the waves are coming in from the sun, and when they hit particulate matter in the atmosphere, as well as molecules, nitrogen molecules, oxygen molecules, etc., in the atmosphere, it gets scattered. It bounces around, and that's the blue light that you see in the sky. That's why the sky is blue. The blue light gets scattered. But most of the visible and the long wavelengths come on down to Earth, and that's called transmitting. It makes it through the atmosphere. And when it gets here, it either gets reflected by objects on the Earth or it gets absorbed by objects on the Earth. And if the wavelength, whatever wavelength is reflected, whatever wavelength matches up to the color, that is what you see. Now, if you're colorblind, I've worked with students who are colorblind, and sometimes the greens and the reds get mixed up. So if you speak specifically with wavelength, it helps keep things a little clearer. But we're going to speak in terms of color. So this object is red because we're just breaking it down into the three primary colors: red, green, and blue. So if this is red, that means it's reflecting red light and absorbing green and blue. What's happening here is transmission. If you have a red filter, if you've ever seen like a camera filter will allow the red to go through and absorb the green and blue light. So the light coming through will look red. So that's transmission. But reflection is what we usually are looking at when we're using satellite imagery. Okay, so every object on Earth, whether it is this sticky notepad or this, let's see, my little notebook here, every object will reflect electromagnetic energy. And so what you're looking at here is something called a graph of spectral signatures. So again, breaking it down into the primary colors, blue, green, and red. And then we show infrared on here as well. We can't see infrared, but we're putting it on our chart. And the y-axis represents the percentage of reflection of all the light coming in. Let's say we've got my little sticky note here. All the light coming in from my window over there hits this sticky pad, and it is reflecting mostly blue. So if I had my sticky pad graphed on here, it would show a higher curve up here in the blue and lower in everything else. So let's look at this grass first. Grass. It reflects low in the blue, reflects higher in the green. That's why we see green when we look at grass or the trees or whatever. Lower in the red, high in the infrared. We can't see the infrared. If we could, when we look at grass and trees and healthy vegetation, we would see whatever color infrared is, but we can't see it. So what we see is this green right here, because it's being the primarily reflecting green. Let's look at artificial turf here. This is the dashed line. You see green with it. It absorbs a lot of infrared. It absorbs a lot of red, and absorbs a lot of blue, but it reflects a lot of green. So if you wanted to know, if you have a satellite going overhead and it gets a picture of a football stadium, it will show up. Our satellites are actually picking up not only blue and green and red visible light, but we have infrared sensors on there, and it tells us how much infrared is being reflected. So that will show low in the infrared, low in red, high in green, and low in blue, unless you're one of these weird places that has the blue football fields or the red football fields. In New Braunfels, they have a red football field. Down in McAllen, there's a little town really close to Mexico, and they have a yellow football field. So provided the actual field is green, then you'll have high reflectance in green. So asphalt, low in everything. It's black. It's absorbing more than it absorbs more than it reflects in any color. So it's black. Clear water is kind of cool. That curve kind of got messed up there. The clear water, it reflects more in the blue and the green, a little bit in the blue and the green, but not a whole lot. But in the infrared, it just absorbs like crazy. And then concrete is high in everything. Concrete is white. If you have a white color, that means it's reflecting everything. So it's going to be high numbers in everything. So keep all of that in mind. And we go back to the Earth imaging satellites. So they're recording the reflected electromagnetic radiation from Earth. We have what we call multispectral sensors on the satellites, which breaks the light into blue, green, red, infrared, microwave, radar, which is radio. And it splits it up into the different segments. We call those bands. Normally what you have are most satellites that we work with go from green to infrared and some radio waves and some microwave sometimes. A lot of times we don't grab the blue because the blue is so easily scattered that the blue imagery gets a lot of haze and a lot of noise to it. But each picture element or pixel holds a value for the amount of electromagnetic energy reflected. So when we say pixel, that is actually short for these two words here, picture element. That's where we got the word pixel, if you were ever wondering. So here we go. We take an image of something on Earth and break it up into the bands. So we have the blue band, the green band, the red band. When you split it up into the bands, it looks black and white. You think, why isn't it blue? It looks black and white. We give those bands a number. Band 1 is green, blue. Band 2 is green. Band 3 is red. Band 4, near infrared. That's what the NIR stands for. We color that kind of black and, not kind of black, but kind of it's kind of a Texas orange right there. Just so we don't get mixed up with blue, green, and red. So the next few slides, we're going to look at Stephen F. Austin State University from 2003 from the QuickBird satellite. That's one of those private industry satellites. It's broken up into, we'll see the natural color, the blue, the green, and the near infrared separate images. So here's the natural color. Look at the football stadium here. And they have a red track around it. This is a parking lot here, asphalt parking lot. This is their intramural fields, which is grass. There's a pond right here. You see the asterisk there, that's a pond. Here's some more natural grass. These trees right through here and over here, these are evergreen trees. And these kind of brownish color, those are, this is from January, so these are deciduous trees. They've lost their leaves, so you're looking at the bare branches there. This is a main street going through town. It's a small town, so you don't see a whole lot of urban areas around here. This is the university with its buildings. So let's move forward. This is the blue reflectivity. This is the blue band. So look what happened to the football stadium. It's bright. The infield or the main field of the football field is bright now. If it is bright, that means it's reflecting a lot in that band. So that means it's reflecting a lot of blue light. So it means you'll see some blue there. It looks kind of bluish. The trees go dark. The evergreen trees get really dark. The grass is dark. So this kind of gives you an idea. If the grass is dark over here and it's bright right there, wonder what's going on. Look what happens to the pond here. You can barely see it. You see what's going on with grass. It's not bright. The streets right here, the street is bright. So it's reflecting a lot of blue. Does that mean we have a blue street? We're looking at the street. It's got a blue color? Maybe. You'll have to look at some of the other ones. So let's go to the green. So the green, we see the track around the stadium is dark. The stands are bright. It's a little bit brighter in the grassy. You can kind of see the trees over here, that they're still dark. The trees are still dark. This pond right here, and there's a pond right here too. This pond right here is not dark. And this grass over here is a little brighter than it was in the blue. And the street right there is still bright. So it's bright in the green, bright in the blue. So let's look at the red. Look what happens to the track. Remember in the natural color, the track was red? Well, here it's just bright white. So that tells us, if we were just looking at this one page, this tells us that that track, it probably is red, even if we didn't see the natural color. Since it was dark in the blue and the green, and it's bright in the red, we know that that's a red track. Let's look at the grasses. Doesn't look much different than the green. And the trees over here, the asphalt's still black here. The pond's still black. This pond over here is brighter than this pond over here. And the street is still bright. So that tells me if it's bright and blue, green, and red, that means it's white color. So that street is probably a concrete mix instead of asphalt. And speaking of asphalt, this parking lot has been dark in each of the red, green, and blue, so that means it's dark. Also, the football field is dark here. So let's go back. Whoops. Let's go back. There's the green. It's a little brighter in the green than it is in the red, the football field. That is right there. But it's brighter in the blue. And if we go to the near infrared, that's really dark. So it tells us that this field is artificial. So look what happens to the grass. Oh my gosh, it just lights up like a Christmas tree. And same thing with this grass over here. And the trees, they're no longer dark. They're a lot brighter. So this is that reflection in the near infrared that we looked at earlier. And look at the ponds. They both went really dark, a lot darker than they were in the red. So this pond is brighter in the red than this one is. That means that this is kind of a muddy, red mud kind of pond. But when you go to near infrared, they both go just as dark as they can be. So that is how we use the different colors of the spectrum to tell us what's going on the Earth. Let's go back and look at our reflectance. So recall what we saw with that football stadium. We had low in the, we had a little bit higher in the blue. So it's probably the grass is probably kind of a blue-green color if you're there in person. So our artificial turf didn't reflect much at all in the infrared, but our trees and the grass was way high in the infrared. Remember, they're bright colors. So what I did is I went in and I grabbed from a pixel in this grass here and a pixel from the artificial turf and graphed those out. So in this one pixel in the artificial turf had a blue value of 197, a green value of 251, a red value of 108, lower, and an infrared value of 178. So see how the green and the blue were much higher than either the red or the infrared. If we look at the grass, we've got blue way down here at 150, green 255, red way down here at 150 again, and way high 480 in the infrared. And so the reason for that is that plants. This is a cross section of a leaf, and the plants are using the sunlight to convert carbon dioxide and water into glucose, which is carbon, hydrogen, and oxygen. So the energy levels that it likes to get from the sun is actually in the blue and the red. It really likes blue and red light. That's the right amount of energy coming in from the sun to help it convert that water and carbon dioxide into food for itself. It doesn't really care much for the green or the near infrared, so that gets sent back out into the atmosphere. So it gets recorded by the imagery. So because we can record these levels, we can do something called an NDVI, which we compare the near infrared to the red values of what's being reflected. And we put it into this index. You don't have to worry about the formula of that. Just know that by comparing how much infrared is being reflected to how much red is being reflected, we can convert it to values between -1 and +1. And we get a map that looks like this. And I'm going to put it, I color-coded it so that anything with a positive number, anything more than 0, gets coded as green, which means it's living, it's doing that photosynthesis thing, and the greener that is, the closer it is to +1, which means you've got the most photosynthesis going on. So we can find where the healthiest vegetation is. And anything with a red color is not living, is not It's not vegetation. So if it's green, it's the greener, the brighter and deeper the green is, the healthier it is. The less green it is, if it's above 1, the less healthy it is. So here's these are called NDVIs, Normalized Difference Vegetation Index. You don't need to know that term. You just need to know that by combining, by having all of the different values of all of the different bands, reflections, we can determine vegetative health. So this shows the contiguous United States. This is May in 1990, May to June, June to July, and you can see what happens to vegetation. And we know this from living in Texas. We actually start losing vegetation in August, and a lot of times things die off by the time we get to September, and then it starts greening up again. But you can see what's going on in the United States, where the green things are. And this company, Sports Turf Mapping from Holland Scientific, they can actually help you if you own a baseball field like this, or if you manage a golf course, or just need to find out what's going on with your vegetative health. They will go out and get a multispectral image at a high resolution for you, and run an NDVI for you, and give you this interpretive map to tell you where your vegetative health is not so great. Well, if you know anything about baseball, you know that it's going to be worn out over here where there's a lot of activity, right here where you've got your second baseman standing and your center fielder. But if you look at this, these are really high values. Even the worst of the grass is at 0.7. It's still pretty close to +1, which is as healthy as you can get. So some other things that we can do with imagery is we can pick up on what's going on with heat being re-emitted from the Earth. Now what happens is you've got the sunlight coming in, and the Earth, it's reflecting a lot of light, but it also absorbs a lot of light. It absorbs a lot of energy coming in from the sun. Where you see the asphalt, remember it's dark on those maps earlier. It's really where anything's dark, is going to be absorbing a lot of electromagnetic energy, and it absorbs and absorbs and absorbs, and it gets really hot, and the Earth is like, I've got to cool myself off. So it starts emitting it. And if you've ever walked across, let's say in August or September, it would be better because it's not quite so blazing hot everywhere. But you're walking across an asphalt parking lot, and you'll feel heat. It feels warmer. You step onto grass. If you step onto a field, you don't feel as much heat coming up from that asphalt. That's because the asphalt is black. It absorbs all that energy coming in, and then it starts re-emitting it because it just heats up so much it can't contain any more heat. Okay, the Earth does that. So what you're going to see in this next slide here, this is in Huntsville, Alabama, hours after sundown, 5 hours after sundown. And the dark areas are going to be cooler. The light areas are warmer. The light areas where the Earth is re-emitting the heat. So this parking lot, this asphalt parking lot, is going to be really hot there. And the grassy areas are cooler. So these buildings, this mall is cooler than what you see here. These are tops of buildings. So those are going to be cooler because they did not probably absorb as much heat as the black tops do. So this is why in a city like Austin, what you're looking at here, this is thermal infrared imagery of the city of Austin. From one of our students at ACC, this was from her capstone project. This is a really good project. I had a lot of fun working with her on this. She took thermal imagery from one of the Landsat, I believe it was Landsat 7, and she looked to find the hottest places in Austin in October. And so where you see the red here, this is, well, let me get you oriented. This is the Colorado River / Lady Bird Lake / Lake Austin and all that. This is North Austin downtown. This is Barton Creek Mall. This is the Miller or Mueller old airport, however people pronounce it. And so if you look at this, the areas where you have water and a lot of grassy areas, this is a park over here with a lot of trees and grass. Those are the cooler places. The hotter places are where you have a lot of development. So what she did here is she took the hottest areas, the reds from here, and she blocked out everything else except for the hottest areas and looked at those. And what she found out is Barton Creek Mall, and let me go to the next slide. It shows it a little better. What she was looking at here, this is the Miller or Mueller residential areas, and all of these roofs are asphalt roofs. They did not use reflective roofing like they did over here. And these are the shops there, and where you see these white roofs, those are reflective roofs. That doesn't give the buildings a chance to absorb that much heat or absorb that much light to convert it to heat. So it reflects the light, so it doesn't get that hot. And if you look, these are shops where you see the hottest places here, the red places, those are actually in the parking lot. Where you see the buildings is not as hot. However, over here in the housing, we can look at this. This is here, this is here. Where you see the housing, you've got these dark asphalt roofs. Well, those houses are just bringing in the heat. They're just absorbing the light from the sun and the energy from the sun. So your air conditioner is really having to work extra if you've got a black asphalt roof. It's not a good idea in the South to have a black asphalt roof. Just good information to know. Whether you take it from this as part of GIS, just remember, hey, when I want to put in a roof, I think I want a white roof, a reflective roof. Also notice this little hole right there. That's the swimming pool up there. Just kind of interesting. So some other applications of remote sensing. You can do some change detection, see what's going on in the Brazilian forest. This is 1975 in Brazil to 1991. This is the Aral Sea in Central Asia, 1977 to 2006. You can see it drying up. And this is, we can also find out what land is being used for. This gives us the ability, this is Montreal, Quebec, you can determine what's on the ground by what's being reflected. And are also able to look at flooded areas and find out, do some mapping to figure out where the deepest parts of the flood were after Hurricane Katrina. And that's going to wrap it up. I have some other things. This is where I usually say, do you have any questions? But since this is a video, I'll just have to say, bring your questions to me via email or send it through a text, and I'll get my answers out to you there. Anyway, I hope you enjoyed this. This is just an interesting site here. But I hope you enjoyed this. I hope you found it informative. I hope you found it helps you with the text. But this is another neat thing here, just to take away with you, is this page. It's called Earth as Art. If you just do a Google for the Earth as Art and NASA, it should take you to a page where they have just really pretty pictures of the Earth from space. And another really neat thing is this. You can see a lot. Sometimes it's live, sometimes it's a replay of the satellite imagery that's coming down to Earth. Sometimes it's, like I said, sometimes it's live. Depends on where the satellite happens to be. But it's called earthnow.usgs.gov. And you hear me typing. I'm trying to go to it right now. Let's see if we've got it live. And what you may have to do is activate Java and see if it will work. Sometimes it works and sometimes it doesn't. So you go to this Earth Now, and you can just Google Earth Now. Come on. It's not wanting to come up for me. But you'll be able to see live images coming from space. Now what happens is when here we go. Let me drag this over to the screen here. So what you'll see is this path. This is the path of the Landsat. This is Landsat 7, and it's a replay from today, from 10:47. So this was about an hour ago from when I'm recording. And so this is what you see. It's coming over Hudson Bay, and that's a lot of ice. And eventually, it's kind of not long from now, it will be coming right over Texas. So, like I said, these things come over several times a day. And the last time that one of these satellites will pass over the continental U.S. will be around 2 to 3 p.m. in the afternoon. And then it spends the rest of the time going around the rest of the world. All right, so I hope you enjoyed that information about imagery. And we'll have another video where you will be able to bring in a non-georeferenced image and georeference it so it shows up where you want it to show up. All right, again, if you have any questions, don't hesitate to send me an email, send me a text, give me a phone call, and we'll talk about it.